Good day, I'm Norman Wappinger. In today's video, we're going to look further at the Euclidean projective line. So we've moved into the projective setting and imposed a Euclidean structure on the projective line, just the one-dimensional projective setting. This is a very simple but fundamental kind of geometrical arena, which ends up sort of figuring in many higher geometries. It's kind of a basic building block of geometry because we're talking about lines through a point. Just all the lines through a single point. Okay, so we're going to talk about the projective quadrants, which we introduced last time, and I'll remind you about this most important formula, the projective triple quad formula, and I'm going to show you how to prove it. Okay. And then we're going to go on and talk a little bit more about the structure of this Euclidean projective line. In particular, we're going to talk about isometries or rotations, sort of natural analogs of translations for the affine line. And we're going to see that if we just observe what's going on, that naturally a lovely algebraic structure emerges on this one-dimensional projective line. So even though it's a very simple situation, it ends up having an algebraic structure as well as a geometrical one. And it will be an algebraic structure that will look quite familiar to you, especially if you've had some familiarity with complex numbers. All right, so the setup is that we're working with the projective line, which are just objects like this, proportions x to y, closed in square brackets. And we're visualizing them in the usual xy affine plane. This is the line through the point 1, 1. This is the line through the point 1, 5. This is the line through the point 5, minus 1, and so on. And we've introduced a Euclidean structure on this projective line by this definition of quadrants. This is how we're going to measure the separation between two lines, say this one and this one. Okay, it's going to be a number. Given two lines, we're going to get a number. And that measurement basically imposes the Euclidean structure on this one-dimensional space. Okay, and here's the definition. It was originally x1, y2 minus x2, y1 squared over x1 squared plus y1 squared, x2 squared plus y2 squared. And you should think about that as almost the simplest possible thing you could do. That's sensible. Because in the numerator is encoded the very criterion that measures whether two lines are equal. Two lines are equal, these ones here, precisely when that number is 0 there. And so we're normalizing that so that it's actually projectively invariant, so it doesn't depend if we scale the two numbers here or the two numbers here. And then we saw that there was this important alternate representation of this projective quadrants as 1 minus x1, x2 plus y1, y2 squared over the same denominator. Okay, so both of these ways of looking at things will be very useful and important. And so, for example, if we have the line 1, 1 and the line 5 minus 1, if we, say, compute things with the first definition, we take x1 times y2 minus x2 times y1. So that's minus 1 minus 5, or minus 6. When we square it, we get 36 in the numerator. And then we have to divide by 1 squared plus 1 squared, which is 2, times 5 squared plus 1 squared, which is 26. So it's 36 over 2 times 26. And I guess there's a factor of 4 that comes out of the 36, and a factor of 4 in the denominator gives us a 13. So this is the projective quadrants between these two lines. All right, so here is this fundamental result that we talked about last time, the projective triple quad formula, the analog of the triple quad formula from the affine situation into this projective situation. This formula right here is also known as the triple spread formula. Okay, that's in the context of rational trigonometry in the plane. So it turns out that exactly the same formula is one of the 5 main formulas of ordinary garden variety trigonometry in the plane once you do it correctly. In other words, once you adopt the point of view of rational trigonometry. But that's actually a two-dimensional theory, which we, strictly speaking, haven't got to yet. because we're still only at the one-dimensional level. So what we're seeing is that this formula, which is going to play a major role in the two-dimensional affine theory, is already occurring here in this one-dimensional projective theory. These geometries are connected with each other. Okay, and here's the formula. We have three projective one-points, A1, A2, A3, the three quadrances between them, and here's the relationship between those three quadrances. The sum of all three squared equals twice the sum of the squares, plus this cubic term, 4 times Q1, Q2, Q3. And we'd like to establish this formula. So to start, we might as well be specific about what the 3 points are. So A1 is x1 to y1, A2 is x2 to y2, A3 is x3 to y3, and we'll express things in terms of those 6 numbers. And what we're going to do is we're going to establish not this formula, but an equivalent, rather shorter version of it, which is asymmetrical. We've seen this for the triple quad formula too. There's the asymmetrical version, which is a bit lopsided, is actually more efficient or shorter. Okay, and that's Q1 plus Q2 minus Q3 squared equals 4Q1 Q2 times 1 minus Q3. This makes it also quite clear that it's very close to the standard triple quad formula. If you just remove that last term there, you just get the usual triple quad formula. Okay, so what we're going to do is we're going to look at this identity. So here's an identity. Behold. It's an identity involving x1 squared plus y1 squared, and then this sort of determinant term, and then another x2 squared plus y2 squared, and another determinant term, and then another x3 squared plus y3 squared, but this time with a minus sign, times another 2 by 2 determinant squared. And then that altogether, that sum of 3 products is, perhaps a bit miraculously, 2 times the product of these 3 expressions. Okay, so this is an identity. In other words, if you expand the left-hand side and you expand the right-hand side, you can see that they're equal. So this is the identity upon which this proof rests. The proof ultimately comes down to the fact that there is this beautiful identity out there in the world. We're using it. Okay, so what do we do to this identity? Well, we square both sides, and then we divide by this expression. And then we're going to see that we're going to get basically this thing here. Why? Because the Q1 is essentially this x2 y3 minus x3 y2 squared divided by this product times this product. So we take the whole thing and divide by these 3 products, then the x1 squared plus y1 squared here will cancel with this one here, and we'll just end up with a Q1 inside the bracket. This term similarly is giving us the Q2 after we divide by this thing, and this thing here giving us the minus Q3. On the right hand side, after we've squared things, there's a 4 here, and then this Q1 is this thing squared divided by, again, that product. The Q2 is this thing squared divided by this product. And finally, this expression here divided by the 2 remaining terms, which I guess are these ones, will be 1 minus Q3. That's the sort of alternate or second formula for the projective quadrants that we had, involving that dot product term. So this is a direct consequence of this beautiful identity once we square it and divide both sides by this common denominator. That's magic, admittedly. So in an exercise, verify this identity. Convince yourself that this identity actually is true. So that proof that I gave you, you can follow on your own with a little bit of work without having to resort to a computer. Of course, another proof would be just to take the whole expression, take everything to the left-hand side, and get your computer to evaluate everything, and it will evaluate everything to 0. Completely automatic kind of proof. But you might well ask, how could we establish this formula in the first place? In other words, how could you have discovered this formula when I asked you to try to discover it in our last video? Alright, so one thing that you could have done is said, well, we have these three quantities, Q1, Q2, and Q3. These expressions involving these x1s, x2s, y1s, and y2s, and so on. One thing we could try is the standard triple quad formula, because it's a kind of triple quad formula. So why don't we apply Archimedes' formula to these three things and see what we get? If they satisfy the standard triple quad formula, you'd expect to get 0. Okay, this is a projective setting. They're not going to satisfy the affine triple quad formula, but nevertheless, when you calculate this thing here, you discover that it simplifies to 4q1, q2, q3. Another kind of miracle occurs. And then you observe that the quantity that you actually want, this S of A, B, C, is just the difference between this thing and 4A, B, C. Okay, another quite different possible approach you could have used was to use some of your understanding of classical trigonometry. Because I gave you a hint last time, I told you that these projective quadrances that we were talking about could be related to classical trigonometry as long as you believe that story, which you probably shouldn't, but let's play along. Because the projective quadrant's QI is actually the square of the sine of a corresponding angle. So if here are three lines, and say this is the theta 1, that angle, then the corresponding projective quadrants would be sine squared of theta 1. So we could use the fact that we know that there's a relationship between the three angles, theta 1, theta 2, and theta 3. So there must be some relationship between the sines, and then we can perhaps figure out the relationship between the square of the sines, and then that will be the projective triple quad formula. So the way you could have proceeded is, first of all, let's just use a little shortcut. Let's say that SI stands for sine of theta I. Okay, we have theta 1, theta 2, theta 3. So if theta 1 plus theta 2 equals theta 3, then if you remember some of your classical trigonometry, then the sine of this thing can be written in terms of sines and cosines of these two. It can be written as sine of theta 1 times cosine theta 2 plus sine of theta 2 times cosine theta 1. I'm using s's and c's instead of sines and cosines. Okay, so this has cosines in it, so what do? Well, we square everything, usual kind of thing. So if we square S3, we'll get the projective quadrant's Q3. If we square this, we get the square of this term plus the square of this term plus twice the product. Okay, but this cosine squared is 1 minus sine squared. So is that one there. So if we bring those to the other side, we get a Q3 minus Q1 times 1 minus Q2, and also minus Q2 times 1 minus Q1. And all of that on the right-hand side will be left with this. And then if we square everything once again, so we get that whole thing squared, we're going to get the square of this, which is 4. The square of this is Q1. The square of the S2 is Q2. And the square of the two cosines are 1 minus Q1 and 1 minus Q2. We get a relation just involving Q1, Q2, and Q3. So you can think about this as an exercise in classical trigonometry. If I just asked you, you have three lines and three angles they form. What's the relationship between the squares of the sines of those three angles? It's the same question. Of course, this thing doesn't quite look like the projective triple quad formula, but it's just a rearrangement of it. So if you just rearrange this, you will see that it's equivalent to the projective triple quad formula. Alright, so please check these arguments if you have some familiarity with classical trig. Now you might say, well, wait a minute, Norman, but you don't believe in classical trig, which is exactly correct. I don't believe in it because the angles are problematic. They involve infinite processes, and these functions, sine and cosine, are problematic because they also involve infinite series, at least the way they're usually presented. But nevertheless, you can see that there's some content here. Although they may not make logical sense the way we usually think about them, and we'll have to talk about that at length at some future time, still we can extract some useful information from them. Of course, there's lots of useful information to be extracted from these things. So the possibility arises that we may still be able to resuscitate sine and cosine in the future, but in some more modest and logically coherent fashion than currently. There are many interesting consequences of this projective triple quad formula. Here is one, a very important consequence. It's a situation that you have when you have three projective one points, and the projective quadrances between two pairs are equal. So if quadrants between A1 and A2 equals the quadrants between A2 and A3, let's say the common value is Q, then the question is, what is the third quadrant in terms of Q? So this equal p quadrances theorem says that in that case, the quadrants between A1 and A3 is either 0 or this quantity, 4 times Q times 1 minus Q. This is quite an important expression in rational trigonometry. 4 times Q times 1 minus Q. Okay, so let's prove this. So we're going to use the projective triple quad formula. Let's let this quadrant be equal to R so that everything has a short form. So we have two quadrants as Q and one quadrant as R. So let's just plug those in to the triple quad formula. There's a Q plus R all squared equals 2 times Q squared plus R squared plus 4 times the product, which will be Q squared times R. What can we deduce from that? Well, we expand things out. Here this is 2Q plus R all squared. Square of the first term is 4Q squared. Twice the product will be 4Q times R. Plus the square of the second term is R squared. Here we have 4Q squared plus 2R squared plus this last term. Okay, there's a 4Q squared on this side and this side. They're going to cancel. There's an R squared here and a 2R squared. When we bring that to the other side, it'll be a single R squared. So there'll be still the 4Q squared R on this side, and if we bring the 4QR on the other side, it'll have a minus sign. So there's 0 on the left-hand side and this on the right-hand side. There's a common factor of R here, which we'll pull out, leaving R plus 4Q squared minus 4Q. So if the product of two things equals 0, then there are two possibilities. Either R equals 0 or this quantity equals 0, which we can write as R equals 4Q minus 4Q squared. And this is 4 times Q times 1 minus Q. So it turns out that this particular polynomial is quite a famous one. It's called the logistic map. It's often written as x goes to 4x times 1 minus x. And we're going to give it a name. We're going to call it S sub 2, capital S sub 2 of x. As a function, as like in calculus, x, y, here's the graph of the function, y equals 4x times 1 minus x. It's a parabola because it's quadratic. It's opening downward because it's minus x squared times something. And it turns out that it goes through 0 and 1, of course, because those are the zeros. And it turns out that it's nicely contained in this sort of 1 by 1 box. Go from 0 to 1 here, and from 0 to 1 here. There's a nice little square box there. And this function just nicely sort of fits inside here. Of course, it extends beyond it. But it's actually the values between 0 and 1 which are critical for this particular application. Okay, so an easy exercise, just to have a play with this particular polynomial, or polynumber, might be a better way of thinking about it. That S2 of 1 is 0, S2 of a half happens to be 1, S2 of a quarter equals 3/4, S3 of 3/4 equals 3/4. So this, for example, is telling you that if you have a projective quadrants of a quarter, which is about like this, actually that corresponds to 30 degrees, and then you have another 30 degrees, the total is 60 degrees, which is the angle analog of projective quadrants of 3/4. So this polynomial S2 of S is in fact one of a whole family of remarkable polynomials. We'll call them the spread polynomials. So S1 of S happens to be S, and here's S2, and you can have a look at S3, S4, and S5, and it keeps on going. And this is a very interesting development in the theory of orthogonal polynomials, which we'll have lots to say about later on. So it turns out that these are sort of remarkable modern improvements on the Chebyshev polynomials. Remarkable that such a thing is possible, but that's what it turns out to be. So we're going to be talking more about this projective triple quad formula, coming back to it. Right now I wanted to switch a little bit to another aspect of this rich one-dimensional projective line. I want to talk a little bit about rotations and things called isometries. And to motivate that, let's have a look at the corresponding affine situation. So we go back to the affine line, A1, with our ordinary quadrants, which is now a capital Q, just given by the difference in coordinates squared. Then this Euclidean structure that's sort of imposed on the affine line by specifying this metrical structure is associated to it some important symmetries. And these symmetries are translations. So what we're talking about here is the possibility of translating points on the affine line in such a way as to preserve quadrants. So here's how we're going to define that. So let's introduce some symbols, t sub k, where k is a rational number. And let's define this combination. If we have an affine one point x right here, and the symbol t sub k beside it on the right, that this combination means the new affine one point x plus k. So we're defining what this particular combination of symbols means. And we'll interpret this as saying, well, this is the result of taking this one point and applying the translation t sub k. We're translating it by k, which is what we're doing geometrically. So if we had a1 here and we translated by 3, well, we would get up to this point a1 prime. If we had a2 here and translated it by 3, we'd get a2 prime. And the key fact about this is that when you take a given translation t sub k and apply it to 2 points a1, a2, the quadrants doesn't change. The initial quadrants, which would here have been 2 squared or 4, is the same as the final quadrants, also 2 squared or 4. It's kind of obvious that just the fact that if you add k to this number and you add k to this number, then they cancel and the quadrants doesn't change. Okay, this property of preserving a quadrants, of doing something and the quadrants is still the same as it was before, even though the points have moved, we call that in mathematics an isometry. It's a special kind of term referred to a situation where we have a geometry with a metrical structure and we're moving things in such a way that the metrical structure is essentially unchanged. Now there's an important additional aspect of these translations, namely that once we multiply by a translation to get another affine one point, there's nothing to stop us from multiplying by another translation, say t sub l. So performing t sub k moves it or translates it by k, and then performing t sub l or multiplying by t sub l is another translation by l. And the combined effect of those two things is a translation by k plus l. So the translations themselves, these symbols, naturally support a simple kind of algebraic structure. You take one translation, combine it or compose it with another translation, and you get another translation, which at the level of the indices is just addition. So the translations have an algebraic structure. You can do t sub k, and then you can do t sub l. It's like multiplying them. We write it like a multiplication because that works with this symbolics that we've introduced of just writing the symbol to the right of what it's acting on. Okay, so with that introduction to the affine situation, we now want to investigate what's the corresponding story for the projective line? It's considerably more subtle there. All right, so let's have a look at the projective line with this Euclidean structure given by this projective quadrants that we've defined. Okay, so we have lines through a point, and we have this projective quadrants that, for example, allows us to define perpendicularity. So in this case, there are also important symmetries, which we might call rotations. Okay, and to motivate that, let's have a look at a couple of special lines. So this line here, it's actually a projective 1 point, but physically it looks like a line. It's given by 1 to 0. And this one is 0 to 1. These are naturally perpendicular, these two. Now another example of perpendicular ones is to take some other line, say A to B, and the corresponding one over here, which is minus B to A. Okay, so the quadrants between these two is equal to 1, and that ensures that they're perpendicular. That's our definition of perpendicularity. Okay, so what we want to get at is a way of rotating this one-dimensional situation. We want to rotate in such a way that this line here goes to this one, and that correspondingly this line here goes to this one. So this is a kind of a familiar situation if you've done a little bit of linear algebra in 2 dimensions. But maybe some of you haven't done that, so let me just sort of show you some formulas. Okay, what we're going to do is we're basically going to encode this rotation, but we're going to do so only at the level of one-dimensional things. So here is a new symbol. It's going to be called rho of A to B, and it's going to represent this rotation here that's in red. Okay, and what the symbol does when you put it to the right of a projective 1 point is it gives you another projective 1 point. But this one's not quite as simple as in the affine case where we just added k to the coordinate. Here we're doing something a little bit more complicated because there's 2 coordinates here, and there's actually also 2 sort of indices or labels to our rotation. So the rule is that we're going to take ax minus by for the first entry, and then the second entry is bx plus ay. Okay, so let's try to convince you that this is a reasonable expression that would encode this rotation that we've got visualized here. Suppose we apply this to the special case where we have 1, 0. If x is 1 and y is 0. That's this line here. What's going to happen? X is 1, y is 0. X is 1, y is 0. We're going to get A to B. We're going to get this line here. So yes, indeed, if we have a 1, 0 over here, then we'd have an A, B over here. What happens if we have a 0, 1 over here? In other words, we're talking about this line. So if x is 0 and y is 1, x is 0, y is 1, then we're going to get over here minus b to a, which is exactly this one here. So if we input 0, 1, we're going to get out minus ba. If we input 1, 0, we're going to get out ab. So this thing does have the same physical effect as what we would like to think is the rotation that sends this thing to AB. Okay, so this could be written using a bit of projective linear algebra, which we haven't yet officially talked about, and we will, but just to connect for some of you I know who know a bit of linear algebra, here's another way of writing the same formula involving a little bit of sort of matrix multiplication. So here's a vector xy, or actually we've sort of made it a matrix. Actually the square brackets in this case, since there's no comma, is going to represent for us a projective matrix. Maybe a slightly new idea. Similarly, this thing here is also a projective matrix. It means that it's supposed to be unchanged if we multiply by a scalar. Alright, so this little matrix, A, B minus BA, which is the 2 by 2 array, there's a way of multiplying this matrix with this matrix to give exactly the new matrix AX minus BY and bx plus ay. Okay, so if you're not familiar with linear algebra, well, you could always watch my Wild and Alge series. Okay, but don't worry, we are going to be talking about matrices and multiplication and so on more formally and officially and correctly and so on. Okay, but I just want to connect, for those of you who know a little bit about that, so I want to connect this formula with this. It's really just taking x, y, and multiplying it by this particular projective matrix. So this rotation of this one-dimensional projective space is encoded by this little matrix. A, B, minus BA. That depends on the line A to B. So that formula that we defined certainly fitted with our geometrical intuition about what a rotation ought to be. But here is the theorem that really solidifies the importance of it. It's called the rotation isometry theorem. That if we denote this symbol, rho A to B, more succinctly by rho, then the quadrants between A1 rho and A2 rho is the same as the quadrants between A1 and A2 for any 2 points A1 and A2 on our projective line. So you take any two lines, compute the quadrants between them, projective quadrants, then you apply this rho, so both of them get rotated, and the new quadrants between them is the same as the old quadrants between them. Exactly the same kind of thing that happens with translation in the affine situation. It preserves quadrants. So this is now deserving to be called an isometry because it preserves quadrants. Okay, we want to prove this. So we introduce A1 and A2 as we usually do, and we write down this side here. Okay, rho is just rho of A to B. So we know how to evaluate A1 times rho. This is AX1 minus BY1. There are the two entries. And then BX1 plus AY1. And the way rho acts on A2, that multiplication there is the same kind of thing. AX2 minus BY2 to BX2 plus AY2. So we are asked to take the quadrants between these two projective 1 points. Okay, what's going to be involved in that quadrants? Well, there's a term that's the numerator. The term in the numerator is this times this minus this times this all squared. So if we take this thing times that one and subtract this one times that one and stare at it for a little while, we can expand things out. And we're going to get, for example, AX1 here with an AY2. That'll be A squared times X1 Y2. And the B squareds here, B squared Y1 X2 will appear. And over here there will be an A squared with an X2 Y1 and a plus B2 plus B squared times X1 Y2. But there will also be some cross terms. For example, AX1 times BX2 with a plus sign, but that will be cancelled with the BX1 times, what did I say? AX2, yes. So the BX1 times AX2 will have a minus sign over here, a plus sign over here, and they will cancel. And similarly, the Y1 and the Y2 term here, with an AB, Y1, Y2 with a minus sign here, and over here, Y1, Y2 with an A and a B, with altogether a plus sign over there, so they will cancel. So this is all that we get. And then there's a squared common here, and there's a b squared common here, and we can see that we can factor this thing as the product of a squared plus b squared times x1 y2 minus x2 y1. So when we take the quadrants of these two things, this is what appears in the numerator, but it ends up being squared. Okay, what about the denominator? Well, we have to take this thing squared plus this thing squared. That's one of the factors. Let's see what that looks like. If we take this thing squared plus this thing squared, well, again, the cross terms cancel, and we get a squared x1 squared, and there's an a squared y1 squared here, so this thing factors as a squared plus b squared, x1 squared plus y1 squared. you might recognize this as an entity that you already know. And there's a corresponding situation for this thing squared plus this thing squared. It also factors in the same kind of way. So that's what you get when we work it out. And then these two terms cancel, and we get the original quadrants between A1 and A2. So this shows us that, yes, indeed, this operation of sort of multiplying by this symbol, the way we've defined it, really does preserve our projective quadrants. It deserves to be called an isometry or a rotation. Okay, so when we were thinking about translations of the affine plane, we noted that we could compose two translations to get a third translation. That basically amounted to addition of the underlying labels for the translations. Something very similar happens here with these rotations if we compose one rotation with another rotation. So if we start with the projective 1 point, x to y, and we multiply by the rotation rho a to b, and then take that projective 1 point and multiply by another rotation, say rho c to d, then we can evaluate that because the first thing is ax minus by to bx plus ay. That's how we define this product here. And we still have to then multiply this by rho c to d. Okay, how do we do that? That's a little bit more complicated. That's going to be also another projective 1 point. Obtained by taking c times the first one minus d times the second. And over here, d times the first plus c times the second. Okay, and then you stare at this, and you see that the x's have coefficient ac minus bd, and the y's on this side have coefficient altogether minus ad plus bc. There's a bc there with a minus sign, so that's all right. And over here, if we sort of factor out the x, there's an x times ad here and plus bc there. And the y terms, there's a plus ac from there and a minus bd from there. And now when we look at this, we see that this is also in the form of a rotation, because this coefficient and this coefficient are the same. And these two coefficients are negatives of each other. That's the same story as over here. This coefficient and this coefficient are the same, and these two are negatives of each other. So we can write this combined rotation as xy acted on by a single rotation, a rho ac minus bd to ad plus bc. And now if we just write down the essence of it, it's really that this rotation followed by this rotation, that combination when you act on by x to y, is the same as this rotation. And what we're getting is really an algebraic structure on our underlying projective line. Because this is just a projective 1 point. And here's another projective 1 point. And what we really have here is a way of multiplying two projective 1 points to give us a third projective 1 point. Now this one times this one equals another one. So our Euclidean structure that we've imposed on the projective line somehow has created a natural multiplicative structure on the underlying projective line. So naturally, it's interesting to ask, well, what does this arithmetic look like? Those of you who are familiar with complex numbers, of course, will say, wait a minute, this is just the way we multiply complex numbers. This is like a plus bi times c plus di is ac minus bd plus I times ad plus bc. So somehow the essential formula of complex numbers is already contained just in this one-dimensional situation. One-dimensional situation. But it's really a one-dimensional version of the multiplication of complex numbers. We're not multiplying vectors here. we're multiplying lines through the origin, or projective 1 points. So next time we're going to investigate this algebraic structure further, and we're going to talk about a big generalization of it. So we're going to look at the same picture but in a wider view, introducing some other metrical structures onto that same projective one line. So our picture gets bigger and bigger. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.